Hello everyone, and welcome to today's video. Today we're going to take a look at section 5.1, the mole and Avogadro's constant. So we know from before that the mass of an atom is very small. So as an example, the mass of one oxygen atom is 2.66 times 10 to the minus 23 grams. Very, very small number. Okay, so the gram is much too large to measure individual atoms. So instead, these scientists have created this Avogadro's number, okay, a specific scientist, to represent large quantities of atoms. So we have 6.02 times 10 to the 23. So this mole that you're going to hear in this unit and upcoming units is just another amount of a substance. You're familiar with grams, you're familiar with kilograms, and now you're going to start to hear the word a mole of a substance. And this was determined to contain 6.02 times 10 to the 23 particles. And if we were to use these values in our equations, that's where things get a bit messy. So that's where we use this Avogadro's constant, okay, in these upcoming calculations, and I'll show you how to do that. When we are sort of using these moles, we have to make sure we're using this correct representative particle. So for elements such as potassium, such as sulfur, such as oxygen, we use this particle of an atom. For a molecule, such as H2O, or for a compound, such as H2O, or perhaps HCl, we need to, these are no longer atoms, so we need to use these molecules to represent these compounds. You're also going to see this term, these formula units, so we use these for ionic solids, such as NaCl, there's your metal and your nonmetal. Or let's say we have something such as copper sulfate. There's your metal and your polyatomic ion. Or perhaps in your question, if you're actually given the ions such as Na plus or NO3 minus. So when we want to convert between an amount in moles and the number of particles, we can use this equation here, which again you will be given on any assessment. Your goal is to understand how to use this equation. So this lowercase n here represents the number of moles. The n is the number of particles, and why that's in quotations is because you could have any one of these particular examples. And then you have Avogadro's number, which is 6.02 times 10 to the 23. The units for this will also be changing depending on your question at hand. So the units for this might be atoms per mole. Atoms per mole. They may also be, let's say you're dealing in a situation with a compound. So these units may change to molecules per mole. And let's say you have perhaps this ionic solid, you might also see these units change to formula units per mole. So that's just recognizing, again, what you're working with in your particular question. Another way to think about this equation here is by using a triangle, okay, the formula triangle. Your n is going to be on the bottom right, your capital N is going to be up top, and your Avogadro's number will be down here. So based off making this triangle is where you can create different equations. So this equation, n equals n over Na, you can see is created because the moles is n over Na. Okay, looking at this, let's say you want to, solve for Na here. Okay, so Na would be equal to capital N, and we use this line, divided by the lowercase n. So we can also create this equation. And let's say you were looking for the number of particles at capital N. Well, because this is on the top and these two are beside each other, this capital N would equal to your moles times your Avogadro's number. So we're going to utilize these three equations today, and I'm going to show you how to do some calculations. Okay, so the first one we're going to try is converting the amount in moles to number of particles. With any of these equations that you do, or these kind of numerical questions, you always want to establish what information you're given and what are you trying to find. So we want to know how many molecules of ammonia, NH3, are present in 4.50 moles of ammonia. So since we're looking for the number of molecules, we can do our N equals question mark, and we're given the number of moles of 4.50. You also know Avogadro's number. Okay, you will have this memorized, I'm sure, by the end of the lesson today. 6.02 times 10 to the 23. This is where you have to double check now. Are the units given in this question, or are the particles given consistent with your compound? If it's asking for how many molecules of ammonia, well, yes, NH3, these are both consistent. So we don't have to do any side work for the time being. Okay, so then what we can do next, we can start with our equation. So we're looking for N. So we can see right here it's at the top. So our number of particles is equal, always start with your formula, is your number of moles times your Avogadro's constant. And here you just simply plug in your values. When you are doing any calculation, you always must ensure you put your units. Okay, what we can actually do here for Avogadro's number, since we're dealing with molecules, we can write this as molecules per mole. I'll just slide this over just a little bit here. Keep your work nice and organized. Okay, so we got a 4.50 mole. We got our 6.02 times 10 to the 23 molecules per mole. And when you write these units, you can see that this mole will cancel with this, and that will give you the value of 2.71 times 10 to the 24. The units that are left are your molecules. And this is where you need to look at your significant digits. Right here we have 4.50. That's the information that's given. That's 3 significant figures. So our answer must also be in 3 significant figures. Okay, so in 4.50 moles of ammonia, there are 2.71 times 10 to the 24 molecules. Very large number, very messy to work with, which is why we like using these moles, because it keeps it nice and simple for us. Okay, so part B of this question is asking us how many atoms in total are there in the sample of 2.71 times 10 to the 24 molecules. So this is where we have to do a little bit of a unit conversion. NH3 here, this is our molecule. If we were to draw a picture of this, a representation, there's your 1 nitrogen, there's 1 hydrogen, 2 hydrogen, and 3 hydrogen. Okay, so this is our molecule, and we have to see, okay, so that's 1 molecule. And what is it comprised of? Well, there's 1 nitrogen, and there are 3 hydrogen. So that means in total, you could also do this by looking at the chemical formula, but here's a visual representation. Okay, so for every 1 molecule, there is going to be 4 atoms. If we know in our sample in this particular question, okay, so we're being asked how many atoms are in this sample. That's what we're looking for. So we'll call that X. And our sample is 2.71 times 10 to the 24 molecules. That's what we got from the previous question. This is where we do our sort of unit conversion, or this ratio, so that we have 4 atoms, as you can see, for every 1 molecule. Okay, so you'll notice when you're doing this conversion, the atoms are on the top and the molecule are on the bottom. That's how you know you did it correctly. And going back to your previous math skills, to solve for this unknown variable, you're just going to cross multiply. So we have x multiplied by 1, which is equal to x. Then you have your 4 multiplied by your 2.71 times 10 to the 24. And when you do this, you're going to get 1.08 times 10 to the 25 atoms. Okay, so in this sample of 4.50 moles, we have 2.71 times 10 to the 24 molecules. And obviously, you're going to have even more atoms, 1.08 times 10 to the 25. Okay, so now let's take a look at converting from the number of particles to the amount in moles. A teaspoon of antacid contains 5.90 times 10 to the 21 formula units. When you see this, that is our number of particles. In this case, we're going to be using these formula units as the particle. Okay, we have calcium carbonate. Okay, we have Ca, this is a metal and non-metal polyatomic. So this is an ionic solid. So that's how we know that our units are consistent, which is what we like. Okay, we want to know how many moles are present. So that's going to be our lowercase n is equal to question mark. You always know Avogadro's constant, which is 6.02 times 10 to the 23. And in this case, because we're working with formula units, the units for Avogadro's constant are now going to change to what you are working with. So this is formula units per mole. So now that you have your given info, you're simply just going to start with your equation, plug in your values, and solve. So if you look back at your triangle, we want to solve for the number of moles. If we look back here, the number of moles is your number of particles divided by Avogadro's constant. So we can take our n is equal to n over Na. The other mistake I see sometimes is students will put a lowercase a, but you got to be careful you don't do that, because you'll know that n in lowercase a is sodium. So please make sure you're taking that time. Even this one, I should probably do a little better. It is a subscript of a. Okay, it's that attention to detail to keep in mind. Okay, we're going to plug in our values. So we got 5.9 times 10 to the 21 formula units. And we're going to divide this by 6.02 times 10 to the 23 formula units per mole. So what's going to happen is that these formula units are going to cancel, and what that does is that allows this mole now, because it's a denominator, to come back up top. And when you do that calculation, you're going to get 9.8 times 10 to the minus 3 moles. So very, very small value. Why are we rounding it to this? If you take a look back here, 5.9 times 10 to the 21. This is going to have 2 significant figures. So our answer is also going to be in 2 significant figures. Okay, so let's take a look at our last example here. So we have a sample of sucrose, C6H12O6, and it contains 2 times 10 to the 35 atoms in total. So we want to find the amount in moles of sucrose. Okay, so first thing we have, if it contains 2 times 10 to the 35 atoms, that is our N value. The first light bulb that should go off in your head right now is you'll notice you're given the number of atoms. You have to ask yourself, is C6H12O6 sucrose an atom? It is not. Okay, so this right here is our molecule. So what we have to do first for this question is later on we need to convert this so that these units are consistent, and I'll show you how to do that. Okay, so we were given 2 times 10 to the 35 atoms. We want to find the number of moles. Okay, and then we know Avogadro's constant is Na, 6.02 times 10 to the 23. Because this sucrose is a molecule, we need to have our Avogadro's constant in terms of molecules per mole. So this is going to be our focus right now in putting these in the correct units in order to keep moving forward. Okay, so our first step is going to be converting the atoms to the molecules. Okay, so we have C6H12O6. So that means we got 6 carbon, we got 12 hydrogen, and you got 6 oxygen. So in total, we have 24 atoms in 1 molecule. Okay, so this is the unit conversion that we're going to perform. Okay, so we need to find the number of molecules. So that we have is X molecules is what we're looking for. And the question we were given is we have 2 times 10 to the 35 atoms. This is equal to, well, in 1 molecule, make sure the units are consistent on the numerator and denominator, we have 24 atoms. Okay, so once again, you got your molecule and molecule, atom and atom. Using your simple math, you're going to cross multiply, and you're going to get 24x. Okay, this first arrow, x times 24, is equal to 1 times 2 times 10 to the 35, which is just this value. Anything times 1 is just itself. In order to solve for this x, we're going to divide by 24. What you do to one side, you do to the other. And you are going to get x is equal to 8 times 10 to the 33 molecules. So now that we have these units, these number of particles for what, again, we're working with here. This is a molecule, so that's why we need the number of molecules. So now we can actually use this and find the number of moles. Okay, so our step 2 here is going to be just that, finding the number of moles. So in order to do that, we're going to take our equation, go look at your triangle. It's our N is equal to N over NA. And our sucrose we have is 8 times 10 to the 33 molecules. And we're going to divide this by Avogadro's constant, which is 6.02 times 10 to the 23. And the units we're going to be using now are molecules per mole. That's going to allow these molecules to cancel. Plug this into your calculator, and you're going to get 1 times 10 to the 10 mole. Why is this simply just 1? If you take a look back at your question, this right here is 1 significant figure. So our final answer will also be in 1 significant figure because we are dividing. When you're dividing and multiplying, you always look at the least amount of sig digs in your question given to you. So that concludes our lesson for today. Thank you all for watching.